Hello and welcome to today's video where we will go through some of the most recent questions from the topic of flight planning. So there are some questions that will need us to calculate some things. So I highly recommend that you grab a notebook if you want to follow today's session properly. So let's jump right into it. I'll try to give you as many tips and exam ready explanations as I can. And let's jump into question number one. So question number one, an aircraft has to fly a distance of 123 nautical miles. The planned time to cover this distance is 93 minutes. Actually, it covers the distance in 41 minutes. So, how fast did the aircraft fly? So this is an extremely simple and straightforward question. However, it has showed up in the exams, so people do flag it as one of the most recent questions in the last time across EASA exams. However, the reason it's here is because it shows an extremely important and a fast principle that you should utilize not only for the exams, but also for your future flying. And this is, of course, the speed factor, which is how fast your aircraft flies per minute. In most cases, when flying GA, you will probably use speed factor of 2 for most of your calculations. It will make flying extremely easy and calculating and using dead reckoning between two waypoints when you need to give estimates to the ATC or fill in your flight navlog. So of course, this question is made specifically for speed factor. As you can see, the distance 123 and the minutes 41, they're actually divisible by each other. So if you divide the distance flown by the minutes it took, we will see that it took us actually 1 minute to fly exactly 3 nautical miles, 123 divided by 41. So if we fly 3 nautical miles per minute, of course, per hour, we will fly 60 times 3, 180 knots. So this is the actual speed that we've flown in order to cover that distance. Even though, realistically, although we planned for almost twice as a little of a speed. So now for question number 2, determine the lowest suitable ICAO IFR cruise level given the track 185 true, variation 5 east, and heading 182 magnetic. This is a great question. This principle and this type of question will come back not only in flight planning, but also in radio navigation, also in general navigation, and actually airlaw. So what you need to do, first of all, of course, is to remember that we always, when we fly east, we fly odd altitudes and flight levels. When we fly west, we fly even flight levels and altitudes. VFR altitudes will have an additional 500 feet, so 3,500, 4,500, and IFR flights follow a whole numbers, 7,000, 8,000, flight level 100, etc., etc. Here, remember that we always used magnetic track in order to determine whether we are flying east or west, odd, or even altitudes. So we need to convert our true track into magnetic track using the variation. The heading is absolutely not necessary for this question. This is there only to distract you. So you can do this very easily, either using the calculations that you have studied before. However, there's a quick way to remember this, and that is variation east, magnetic least. In that case, that means that if the variation is east, 5 east in this case, that means our magnetic track will be least lower than the true track. So of course, 185 minus 5, this gives us 180. So 180 sits in the region of flying west, and this means that we will use an even flight level. So as you can see, we have 2 even flight levels, flight level 280 and flight level 300. So what you need to remember here, that there is a specific case, so flight level 290. So first things first, the question asks about the lowest suitable IFR flight cruiser level. The lowest is 280. However, also remember that RVSM airspace, reduced vertical separation minima space, starts from level 290, and this is where, if aircraft are suitably equipped, so they have the necessary equipment, they can fly with only 1,000 feet separation between each other, or 2,000 flying in the same direction. However, if not, then the separation between these two flights has to be 2,000 feet flying opposite and 4,000 feet flying in the same direction. So these flight levels starting from 290 will always be odd. So in this case, flight level 280 will be the correct answer. And now going into question number 3. So this will be some simple as altimetry. However, altimetry similarly is a very important topic. You'll see questions with altimetry in MET, flight planning, GNAV, performance, and sometimes even ops. So it's good to master the topic. So given the following information, you have to calculate the true altitude of the aircraft to ensure the minimum obstacle clearance is available. And of course, in this case, first of all, remember that when you are doing your temperature corrections, which is always the trickiest one, and there is a station elevation or aerodrome elevation, always subtract it, because we only use the temperature correction to the actual portion of air above a certain place, mountain, station, or aerodrome. Also remember that the ICAO deviation is negative, in this case minus 15 degrees Celsius. Then of course the altitude, the true altitude will be decreased, because when flying high to low temperature, watch out below, meaning the true altitude decreases. And when the ICAO deviation is positive, of course this will be the opposite. First of all, what you need to do in this case, you change your flight level into altitude. So of course we can see that we have QNH of 1004 comparing to standard 1013. So we have 9 hectopascals of difference times 30, 270 feet. And of course, if the aerodrome QNH is higher, then our altitude is decreased, so 5,000 minus 270. And then we need to use the temperature correction, so using the 4% rule. For every 1,000, 4% times the ICAO deviation, we can very easily calculate by multiplying the altitude, which will be roughly 3,200, so 3.2 times 4, and our ICAO deviation, which is minus 15. And if you do these calculations correctly, the answer you should get will be 4,530 feet. So remember, the trickiest part of these questions is always remembering to subtract your aerodrome elevation before doing the temperature correction calculation, and remembering that when ICAO deviation is negative, in this case minus 15 degrees, it will always be decreased. When positive, it will be increased. And now for question number 4. So given the following information, departure aerodrome elevation 2,500, top of climb 1,800, flight level 185, sorry, rate of climb 1,500, and then the given QNH, how long does it take to reach our top of climb? Of course, for these situations, again, you need to change your flight level into altitude, because we need to calculate how high we are actually realistically climbing. So we have our flight level 1,000, flight level 185, which is basically a pressure altitude of 18,500 to a reference QNH of 1013, which is the standard pressure setting. So now if we calculate this, if we change this to an altitude, we can see that our QNH at the aerodrome is 995, which will be 18 hectopascals below our standard pressure setting. So 18 times 30, again, as we need to check the difference in the altitude and flight level. So once you get your answer, you need to subtract it from flight level 185 in order to get the actual true altitude, and then further subtract your departure airport elevation 2,500 feet from this in order to get the actual altitude that we are climbing to through the air. Now, of course, divided by 1,500, and the answer you should get should be 10.3. But remember, the minutes, of course, are not up to 100. They are to 60, meaning 10.3 will be 10 minutes and 1/3 of a minute. So 10 minutes and 20 seconds, meaning that 10 minutes will be the closest answer in this particular case. Here also remember that if there is wind given, you need to also include the wind calculations, for example, for headwind or tailwind. So when you are descending, always take the wind that is halfway through your descent. And when you're climbing, always take the wind information from 2/3 of your climb. So if you're climbing to 10,000 feet, take the wind from 6,600. If you're descending from 10,000 feet to 0, take the wind from 5,000 feet. And now question number 5. So this is a topic that also covers some radio navigation, but it's extremely important to know how it works, especially for the real IFR exams and flying, but also, of course, for the ATPL exams. So the LPV gives us what type of guidance with the performance of a localizer, and the protected area is smaller or greater. LPV is a type of an approach, so it's a precision-like approach, localizer performance with vertical guidance. In most cases, this is flown using GPS signal, so the GPS is guiding us both laterally and vertically towards the airport. This is a very precise approach, the most precise type of GPS approaches that we can fly. Remember the main difference between LPV and LNAV VNAV, which is the second type of approach that is quite popular, flown using the in the PBN spectrum, will be that the LPV is angular, so it's very much like an ILS. It gets more sensitive the closer you get. LNAV VNAV has lateral navigation, so it will show you cross track in most cases, and it will not get more sensitive the closer you fly. Of course, LPV gives you lateral guidance with the performance of a localizer, and the predicted area is smaller compared to other types of approaches, except for, of course, ILS, GLS, and MLS, the classic non-precision approaches. Because this approach is very accurate, it needs smaller margins of error. And now for our last question here. So this is a question about IFR altitudes, which you will for sure see one type of these questions in your exams. And so I highly recommend that you study all the different altitudes that we will use. This is very valuable for flight planning, airlaw, and ops, and also your IFR flying phase of the training. And you'll for sure see this type of a question in one way or the other during our exams. So the ICAO Doc 8168, which is also a IFR Bible, states that the specific altitudes are established for each aerodrome and provide at least 1,000 feet obstacle clearance within 25 nautical miles of the navigation 8 or other fixed, intermediate, or initial associated with the approach. Which of the following abbreviations is used for such altitudes? Of course, this will be our minimum sector altitude, or the MSA. This is the one that we'll most often see on the instrument charts in a big circle around the airport. Sometimes they can have sectors, so that on the eastern side and the western side, these MSAs can be divided and can be slightly different. There is also a little trap. Remember that if the question refers specifically to this altitude in a radius of 25 nautical miles, but only within a certain fix, in most cases initial approach fix, this will in most cases be a TAA. So our terminal approach area looks very similar to an MSA. However, it is not based on the navigation 8 and only starts on some kind of fix, in most cases in our initial approach fix. All of these, however, are worth studying. So minimum en route altitude MEA, for example, this is the one that will ensure that you have continuous radio reception and nav aid reception throughout your runway. And of course, MOCA, MCA, and there are grid MORAs and MORAs. I highly recommend that you study all of them. However, we can talk about these in a next video. Thank you so much for tuning in for today's quick walk through these 6 questions of flight planning. I wish you all the best with your exams. I hope to see you in the next video, and have a fantastic rest of your day. Bye-bye.